Finding the shortest path across a two-dimensional grid is a solved mathematical problem, but forcing a physical robot with mass, friction, and motor limits to drive that exact digital path is entirely different. When we feed a standard pixelated grid path directly into a robot's motors, the system often fails. Instead, the physical hardware tries to execute instantaneous changes in heading, forcing the motors to abruptly halt and reaccelerate. This exposes the core engineering challenge, bridging the gap between abstract algorithmic geometry and the continuous motion required by physics. To solve this without risking hardware, developers use a model-in-the-loop simulation framework. This creates a closed environment where both the control software and the physical robot are represented as mathematical models. This setup allows for rapid testing, ensuring that a logic error leads to a crashed simulation rather than a physically destroyed hardware prototype. Validating these mathematical models in an isolated digital environment provides a safety buffer before any code is deployed to physical hardware. The software itself follows a modular architecture, organized into 8 Python packages that can be tested independently. This data flow pipeline begins with the environment model passing occupancy data into the A-star path planner. The path filters through a waypoint pruner and trajectory generator. Finally, the motion controller translates coordinates, and the robot model feeds its state back, closing the loop. Decoupling the logic from the hardware in this way allows for the aggressive optimization of individual components in the navigation stack. A standard A-star planner generates a waypoint for every single grid cell, creating hundreds of redundant points, even along a perfectly straight line. To eliminate this redundancy, the system applies a strategy called line-of-sight pruning. This check uses Bressenham rasterization. If a straight line can be drawn between 2 distant nodes without hitting an obstacle, like the green path seen here, the algorithm accepts the connection and deletes the unnecessary points in between. The raw path on the left contains 29 waypoints, while the pruned version on the right uses only 6. This filter reduces total waypoint count by up to 91%, preventing the erratic motor behavior caused by tiny, unnecessary path adjustments. This brutal simplification up front directly reduces the total computational load on the motion control layer. Recalculating a path from scratch every time a robot navigates between familiar locations is a waste of processing time. To solve this, the framework uses convex cell decomposition. It divides the map into safe regions and pre-calculates the paths between their centers. By retrieving these cached segments from memory rather than rerunning the search, the system achieves a 9.3 times speedup in query retrieval. However, even an optimized path still has sharp corners. For a physical robot, these represent sharp vertices that require it to stop and pivot. The system uses B-spline interpolation to round out those sharp corners into the smooth blue trajectory seen here. The remaining waypoints act as control points, ensuring continuous curvature. This allows the robot to maintain momentum, reducing trajectory tracking errors by 48%. Spatial memory addresses algorithmic latency, while mathematical smoothing manages the mechanical limits of the steering hardware. In the motion control layer, Model Predictive Control, or MPC, is often considered the industry standard because of its ability to predict future states. When tracking a simple point mass physics model, MPC lives up to its reputation, outperforming standard controllers by over 50%. But real robots like the Turtlebot use differential drive systems. They operate as non-holonomic unicycles, where forward speed and rotational speed are strictly linked. This creates a paradox. In these error charts for a unicycle model, the sophisticated MPC in orange shows massive deviations, while the simpler PID controller in blue hugs the path. The MPC produces spiky, high-frequency signals, struggling to maintain speed through curves. This failure occurs because the linear approximations used by this specific MPC break down when they try to account for the complex, nonlinear physics of a robot turning. The PID controller succeeds because it uses exact trigonometric feedback to handle heading errors, producing the smooth, unbroken curvature profiles seen in these charts. A theoretically superior optimization algorithm is counterproductive if it ignores the fundamental constraints of the physical robot it is trying to control. While highly optimized, the current framework relies on the assumption of a static two-dimensional map. In a physical deployment, the robot faces dynamic obstacles and sensor noise that can disrupt perfect state estimation. There is also a computational cost. The MPC currently requires 57 times more processing time per step than the PID controller. To improve this, the control system needs to transition to a constrained solver that can rigorously enforce kinematic boundaries. The system also requires an extended Kalman filter to manage the spatial drift that occurs in the real world. The final goal is to integrate this Python architecture into a middleware like ROS2 for seamless hardware deployment. While pure simulation validates the logic of the pipeline, the final step toward autonomy involves testing these models against the noise and dynamic variables of the physical world.